In the name of Allah, the most gracious, the most merciful, praise be to Allah upon the messenger of Allah, our master Muhammad, and upon his family and companions all. O Allah, teach us what benefits us and benefit us with what you have taught us and increase us in knowledge. In the last episode, we explained the low impedance differential protection for the bus bar in the case of a single bus bar, and we discussed the fault scenarios related. We moved on to a single bus bar with a cable circuit breaker having 2 CTs at the ends. We explained the fault scenarios. Then we transitioned to a single bus bar with 1 CT on one end. I'll detail this case today. In normal conditions, with a single bus bar and 1 cable CT, the relay adds 200 amps to zone 1 as it enters and subtracts 200 amps from zone 2 as it exits, making the differential current 0 in both zones. The relay decides this through its algorithm, not the CT connection. Under normal conditions, with a single bus bar and 1 cable CT, the relay adds 200 amps to zone 1 and subtracts the same from zone 2, resulting in a differential current of 0 in both zones. The relay, not the CT connection, decides this through its algorithm. In a fault scenario with 9400 amps on bus bar 2, all feeders change direction to supply the fault. Feeders on bus bar 1 supply the fault through the cable CT with 5000 amps flowing from left to right. This 5000 amps exits zone 1 and enters zone 2, affecting the differential current. Zone 1 remains 0, while zone 2 becomes 9400 amps. In the case of a fault with the value of 9400 amps on bus bar 2, we will notice that all feeders will change their current direction to supply the fault area. Just that all feeders on bus bar 1 will go to supply the fault area through the cable CT. You can see that 5000 amps are flowing from left to right to supply the fault area in bus bar 2. Since this 5000 amps is leaving zone 1, bus bar 1, and entering zone 2, it will be subtracted from zone 1's differential current and added to zone 2's. Zone 1's differential current stays 0. Zone 2's becomes 9400 amps. Thus, the relay trips to disconnect bus bar 2's breakers and the cable breaker, while bus bar 1 stays stable. If a fault hits bus bar 1, zone 2's differential current stays 9400 amps. This is due to the 5000 amps direction through the cable CT mimicking a fault on bus bar 2. The relay locates the fault on bus bar 1 or 2 by the current direction through the cable CT. If current through the cable CT is right to left, the fault is on bus bar 1. Conversely, if left to right, the fault is on bus bar 2. On bus bar 1, between the cable CT and the cable circuit breaker, the differential current in zone 2 remains 9400 amps. This is because the 5000 amps through the cable CT act as if the fault is on bus bar 2. The relay determines the fault location based on the current direction through the cable CT. If the current flows right to left, the fault is on bus bar 1. If it flows left to right, the fault is on bus bar 2. Since the 5000 amps flowed from bus bar 1 to bus bar 2, moving left to right, the relay assumes the fault is on bus bar 2. Thus, the differential current on bus bar 2 is 9400 amps, while on bus bar 1 it remains 0. The relay issues a trip signal to disconnect all circuit breakers related to bus bar 2, including the cable circuit breaker. Since the fault current of 5000 amps flowed from bus bar 1 to bus bar 2, meaning it moved from left to right, the relay assumed that the fault was on bus bar 2. Therefore, the differential current on bus bar 2 was 9400 amps, while the differential current on bus bar 1 remained at 0. This means that the relay issued a trip signal to disconnect all circuit breakers related to bus bar 2, along with the cable circuit breaker. In this case, the fault area was not completely isolated. It was only isolated from bus bar 2, but it continued to be fed from bus bar 1. This is incorrect. So, what is the solution to protect the area between the cable CT and the cable circuit breaker? The solution will be through implementing what is called cable blocking, which is based on the principle of cancelling the value of the current coming from the cable CT in the event of a fault occurring on the bus bar. This is done after a time delay known as the circuit breaker reclaim time, which is expected to include the time it takes to open the breaker and the time to extinguish the electrical arc. This means if a fault is between the cable CT and the cable circuit breaker, the signal activates the circuit breaker reclaim time set to 120 milliseconds. If the fault persists, the relay cancels the cable CT current from zone 1 calculations. As the differential current rises, the relay trips remaining breakers for bus bar 1 and the cable. This prevents the fault from being fed by other sources. The relay cancels the cable CT current from zone 1 calculations. As the differential current rises, arises, the relay trips remaining breakers for bus bar 1 and the cable. Isolate the fault by isolating bus bar 2, then bus bar 1 to prevent feeding from other sources. If the cable is open and a fault occurs between the circuit breaker and CT, find differential and restraining currents for each zone and plot them on. If a fault occurs between the cable circuit breaker and the cable CT, we find the differential and restraining currents for each zone and plot them on the curve. In zone 1, the differential current is 0 and the restraining current is 10 kA, falling below the curve, indicating no trip signal and no reclaim time start. In zone 2, the differential current is 5 kA and the restraining current is 10 kA, also below the curve, meaning no trip signal and no reclaim time start. Thus, if the cable circuit breaker is open and a fault occurs between the cable CT and the circuit breaker, neither zone 1 nor zone 2 protection will detect it. This means that the relay did not issue a trip signal and that the circuit breaker reclaim time did not start at all. The value of the differential current in zone 2 will be 5 kA, while the value of the restraining current will be 10 kA. The same applies when we plot these points on the differential characteristic curve. We will notice that this point falls below the operating curve, which means that the differential current or the differential relay in zone 2 did not issue a trip signal either, and the circuit breaker reclaim time did not start at all. The result is that if the cable circuit breaker is open and a fault occurs at that moment between the cable CT and the cable circuit breaker, neither zone 1 protection nor zone 2 protection will detect it. How do we protect this area? Cable blocking cancels the current from the cable CT when the circuit breaker is open. In the algorithm, differential and restraining currents in zone 1 become 5 kA. Plotting shows it above the curve, issuing a trip signal. The restraining current is 0 and the differential current is 5 kA, placing it below the operating curve, meaning stability. In a single cable CT setup, connect the auxiliary contact of the circuit breaker to the relay to detect faults between the open breaker and the cable CT. Also 5 kiloamperes, and when applying this point to, we will notice that the point is located above the curve, and this means that it will issue a signal as for the value of the will be 0 and the value will be 5 kiloamperes, and this point will be located below the operating curve, and this means that it will remain stable. Therefore, we conclude that if there is a cable configuration with only one cable CT installed, it is very important to connect the auxiliary contact of the cable circuit breaker to the relay so that the relay can detect any faults occurring between the open circuit breaker and the cable CT. Ensure the circuit breaker positions are correctly connected to the relay to avoid incorrect operation of the protection system. Supervision within the relay should monitor and detect circuit breaker states to identify undefined conditions. Undefined conditions occur when the relay indicates the circuit breaker is both open and closed, such as connections between input 1 and 1 or input 0 and 0. If detected, the relay should issue an alert. This is often unnecessary if there is a connection on both cable ends. Undefined conditions are those situations where the relay indicates that the circuit breaker is both open and closed at the same time, such as when it is connected to the relay between input 1 and 1, or when it indicates that the circuit breaker is open and closed simultaneously, like being connected between input 0 and 0. These situations are referred to as undefined conditions. If any of these undefined conditions are detected, the relay should issue an alert. This is something we often do not need if there is a connection on both ends of the cable. These situations are called undefined conditions. If any of these undefined conditions regarding the positions are met, the relay should issue an alert. This is something we often do not need if there is a connection on both ends of the cable. The revival of a nation, a remarkable journey indeed. The challenge is ensuring a defined circuit breaker position if the DC supply to control circuits is lost. The last position is stored in the relay, but an undefined position means the breaker is neither open nor closed. The relay algorithm prioritizes a closed state and issues two alarms, igerator and switching prohibited. The latter alerts that the protection system sees the last stored position as correct unless manually changed. If the breaker position changes, the relay may not recognize it. If the circuit breaker seems both open and closed, the relay sees it as closed. The relay issues two alarms, ignorator and switching prohibited. The latter warns that the system views the last stored position as correct unless changed. Unrecognized changes may cause relay errors. The relay can use the signal within the protection system, done through a system called... The second signal is called switching prohibited, and the reason for the appearance of the switching prohibited signal is to alert that as long as no one has changed the position of the circuit breaker, the protection system currently sees the correct state of the circuit breaker, which is the last position stored in it. This means that if you see this signal and then change the position of the circuit breaker, the relay has not recognized the new position of the circuit breaker. This could lead to incorrect operation of the relay. There is an option within the relay that allows the signal to perform a function for the protection system, and this can be done through a system called... This could cause incorrect relay operation. The relay has a signal option. Only if DC supply is lost, it should not activate in real situations. If the circuit breaker seems reversed, it appears open but is closed. The bot is called Accept Isolator Alarm. The system operates done only in the event of losing the DC supply, but it should never operate in a real situation because that would cause incorrect functioning of the protection system. Now, what will happen during normal load conditions if the position of the circuit breaker connected to the relay is reversed? This means that it appears to the relay that the circuit breaker is open, but in reality, it is closed. Determine and plot differential and restrained currents. Relay cancels cabular CT current with breaker open. Zone 1, 200A differential, dan bias A, sin dash A, 1KA restrained. Low differential triggers alarm. Zone 2, 200A differential, 1200A restrained, triggers alarm. Alarm prevents relay errors. Since there is a low differential current that has persisted for a long time, the relay will issue what is called a differential current alarm. There is an option to block the protection system. As for Zone 2, the incoming current value from the cabular CT will also be cancelled, so the differential current will be 200 amperes, and the restrained current on Zone 2 will be 1200 amperes. Therefore, Zone 2 will also issue what is called a differential current alarm. There is an option to create a blockless system, which means that the differential current supervision is capable of detecting incorrect positions of the circuit breaker. Thus, the differential current alarm is an important signal that cannot be ignored to prevent incorrect operation of the relay. Melhem, Nation's Renaissance. Now, what if only one phase is received by the relay as closed while the other phases are open on the same state breaker? In this case, if the relay receives that only one phase is closed, it must assume that all three phases are also closed, as if the positions of the three phases are connected to an OR gate. This means that the relay does not recognize the open signal unless the positions of the three phases are open, as if they were mounted on an AND gate. Therefore, if the open signal arrives from only one phase, the relay hides it. If we assume that we are performing maintenance on one of the cables, we then open the circuit breaker for this feeder and install a temporary grounding cable, also known as a portable earth cable, on the cable itself to avoid any incorrect operation of the circuit breaker during maintenance. If the circuit breaker is accidentally closed, the fault current will pass through this temporary cable and not affect the workers. If the workers finish their work and this temporary grounding cable is not removed by mistake and the circuit breaker is also closed, this situation is referred to as a switch into fault situation, meaning the circuit breaker is closed on a pre-existing fault. In this case, the circuit breaker must trip instantly and without any time delay. The main issue is that busbar protection sees the fault as internal due to an electrical arc when closing the circuit breaker. The circuit breaker position wasn't recognized as closed and the current value was ignored. Busbar protection incorrectly trips all breakers for a feeder fault. Prevent this by inputting a circuit breaker close command into the relay. If a fault occurs, delay busbar protection to wait for the CT current. The busbar protection will issue a trip signal for all breakers on the feeder before recognizing the breaker as closed. This is incorrect. We must inform busbar protection to treat a closing breaker as closed. Input astan a circuit breaker, close command into the relay. If a fault occurs with the close command, delay busbar protection to wait for CT current. The fault current and close command act like an AND gate, activating delay if a fault occurs. For line protection, it speeds up tripping. For busbar, it delays. Close command refers to any closing signal, manual, remote, SCADA, or control unit. In summary, CT location determines each protection zone's start and end, and we explained. It's as if the fault current and the circuit breaker close command are essentially connected to an A&D gate, so it activates this time delay if a fault occurs with the circuit breaker close command present. For line protection, this specifically means speeding up the tripping process, while for busbar protection, it in particular means delaying the trip. The term close command refers to any closing signal for the circuit breaker, whether it comes from a manual close, remote close, SCADA close, or even from the control unit. So far, we have explained that the location of the CT determines the beginning and end of each protection zone, and then we moved on to explain how many busbar protection zones do you expect to see in this picture? And it is monitored by 2 Cabler CTs. Then we moved on to explain the single bus bar with a Cabler circuit breaker monitored by 1 Cabler CT. Now we will move on to explain the double bus bar system. Can you guess how many bus bar protection zones are shown in this picture? The answer is the one in red and the one in blue, each with its own characteristics. Here, we will present the first question used in calculations and the answer, is it used in the calculations for zone 1 or in the calculations for zone 2? Answer. Welcome. The cabler current is used for zone 1 and zone 2 calculations if the cabler is closed or current flows to it with no intertripping activations. Feeder current usage depends on busbar isolator positions. Closed busbar 1 isolator means zone 1. Closed busbar 2 isolator means zone 2. For a zone 2 fault, trip all busbar 2 breakers to isolate it. Trip breaker 1 and breaker 4 as their busbar 2 isolator is closed. Also, trip the cabler circuit breaker since busbar 1 feeders contribute to the fault through it. The intertripping system decides which breakers to trip during a busbar fault. The answer is that the appropriate zones can be used in the calculations based on the positions of the busbar isolators. If busbar 1's isolator is closed, the feeder current is used in the calculations for zone 1. However, if busbar 2's isolator is closed, the feeder current is used in the calculations for zone 2. If a fault occurs in zone 2, as shown in this picture, I must trip all the breakers connected to busbar 2 to isolate this fault. The breakers that need to be tripped are breaker 1 and breaker 4 because busbar 2's isolator for them is closed. We will also need to trip the cabler circuit breaker because the feeders connected to busbar 1 will contribute to feeding the fault through the cabler circuit breaker. The intertripping system is what distinguishes and determines which breakers should be tripped at the moment a fault occurs on the busbar. Therefore, 3 breakers need to be tripped. Breakers 1 and 4 for the feeders and the bus coupler circuit breaker. The bus coupler breaker, common to zone 1 and zone 2, must always trip to prevent faults from being fed between busbar 1 and busbar 2 through the cabler circuit breaker. Ensure the busbar isolator's positions to the relay are correct to avoid incorrect busbar protection operation. A monitoring system should detect undefined isolator positions, as mentioned with the cabler circuit breaker. Store the last isolator position received by the relay in case of DC auxiliary supply loss, as previously discussed. A special algorithm for the accept isolation alarm is used, but the isolator close command is not required here, unlike with the cabler circuit breaker. Instead, use the isolator normally open auxiliary contact. During a load transfer between busbar 1 and busbar 2, both busbar isolators will be closed. To prevent incorrect operation of the busbar protection system, a monitoring system should supervise isolator positions to detect undefined states. Store the last relay received isolator position in case of DC auxiliary supply loss. A special algorithm for the accept isolation alarm is used, but the isolator close command is unnecessary. Instead, use the isolator normally open auxiliary contact. During a load transfer, both busbar isolators will be closed, creating a single busbar protection zone. How will the protection behave in this situation? Similarly, a special algorithm for the accept isolation alarm is used here, but the isolator close command is not used or required in this case as we did before with the cabler circuit breaker. Instead, the isolator normally open auxiliary contact is used at D. Now, what if I perform a load transfer from busbar 1 to busbar 2 or vice versa? In this case, both busbar isolators will be in a closed state. So how does the busbar protection behave in this case? Busbar protection is crucial in electrical systems designed to detect faults and prevent damage. In this situation, both will be closed and connected to each other, resulting in a single busbar protection zone. This protection ensures the safety and reliability of the power distribution network. Consider a scenario where a fault occurs. The busbar protection will isolate the fault, maintaining system stability. Now let's assume if a fault occurs on busbar 1 at the moment of load transfer, then all the feeders connected to busbar 1 and those on busbar 2 will contribute to feeding this fault. Since the zone interconnection is essentially a combination of zone 1 and zone 2, and previously the cabler current was added to one zone and subtracted from the other, now 1,000 amps will be added to this zone and subtracted from itself. This will cause me a big problem. Therefore, when calculating the value of the differential current for this zone interconnection, the 2,000 amps coming from the cabular CT will be added and then subtracted from the same zone again. Consequently, the value of the differential current will be 4,000 amps, while the value of the strain current in this case will be 8,000 amps. When applying the values of differential current and restraint current to the differential characteristic curve, we will notice that the point falls under the operating stage, which means that the relay unfortunately will not detect this fault. This issue can be easily resolved by cancelling the current value coming from the cabular CT during a load transfer, or what is called the cabular circuit breaker bypass. So, in summary so far, by bus, so that's the bottom line. We are discontinuing the reading from the calculations in the following three specific cases. Specifically, the first case is when an internal fault occurs on the bus bar. In particular, the second case is when it is open or condition, while the third case is when a load transfer occurs during a busbar fault, the cable current is cancelled, resulting in a differential current of 4,000 amps and a restraint current also at 4,000 amps, down from 8,000 amps. Applying these to the differential characteristic curve shows the point in the operating region, triggering the differential protection trip signal, which is desired. In a double busbar system with section isolators, there are 4 busbar protection zones. When applying the values of differential and restraint current to the differential characteristic curve, we will notice that the point falls above the curve in the operating region, which means that the differential protection will issue a trip signal, which is the desired outcome. Now, in the case of the double busbar system with section isolators, how many busbar protection zones do you expect in this case? The number of busbar protection zones in this case is 4 and B, 1A, 1B, and 2A, 2B, as shown in this diagram, where each zone is colored differently to distinguish them from one another. If these are closed, then the number of busbars in this case will be 3. With a double busbar system, if the busbar CT is on the line side and a fault occurs between it and the circuit breaker, busbar protection is affected. If busbar protection trips breakers, the fault continues from the remote breaker. An inter-tripping signal must be sent to isolate it. If the busbar CT is on the busbar side and a fault occurs between it and the circuit breaker, busbar protection is unaffected as the fault is outside its boundaries. The fault is within the line zone protection. This fault is now within the busbar protection zone, defined by the busbar CT position. If the busbar protection trips all related breakers, the fault will still be fed from the remote circuit breaker. An inter-tripping signal is needed. If the busbar CT is on the busbar side and a fault occurs between it and the circuit breaker, the busbar protection won't be affected. It's within the line zone protection, but outside the busbar zone protection. If the line protection trips for this fault, it will open the local and remote circuit breakers. The fault will continue to be fed from the adjacent line connected to the busbar, and the bus section overcurrent may activate. If the busbar CT is placed on the busbar side and a fault occurs between the busbar CT and the circuit breaker, then the busbar protection in this case will not be affected by this fault because it will be considered outside its boundaries. Notice in this picture how the fault location falls within the line zone protection, which is the blue area, while it is outside the boundaries of the yellow and blue areas. This is the busbar zone protection. If the line protection issues a trip decision for this type of fault, it will open the local circuit breaker and the remote in circuit breaker. However, in this case, the fault will continue to be fed from the adjacent line that is connected to the same busbar. The bus section overcurrent may also be activated for this same fault because the lines that will contribute to feeding this fault will pass through this bus section circuit breaker. If the busbar CT is positioned to be effective, then if a fault occurs there, both the busbar protection and the feeder protection will activate simultaneously. The busbar will trip all breakers that could contribute to feeding this fault, while the local circuit breaker and the remote end circuit breaker will also trip. The fault is completely isolated as desired. This table illustrates the summary of the impact of the CT installation location on sensitivity and speed. Ideally, the CT should be installed in a way that overlaps. If the busbar CT is installed on the busbar side without overlap, then it becomes necessary to install additional protection. This is end fault protection. The local circuit breaker and the remote end circuit breaker will trip, thus completely isolating the fault. This table summarizes the impact of the CT installation location on sensitivity and speed. A preferred scenario for using CT is when it is installed in a way that achieves overlapping, whether in a single or multiple breaker setup or in a 1.5 breaker busbar. If the busbar CT is installed on the busbar side without any overlap, then it becomes necessary for me to install additional protection to avoid any incorrect operation. This additional protection is known as the end fault protection function, We will finish opening the control for the above protection functions. Let's assume there is a circuit breaker open for over 120 milliseconds, exceeding the arc extinction time. Then, a fault happens between the circuit breaker and the CT. The trip signal from the end fault protection will initiate remote tripping if the fault feed is from its side. It also does inter-tripping on all breakers on this feeder. Returning to the previous fault between the bus bar CT and breaker, where the bus bar CT was above the breaker, the end fault protection will activate bus bar inter-tripping logic, tripping all breakers potentially feeding the fault. End fault protection activated as two conditions were met. First, CT current reading is higher than setting. Second, breaker is open. For the same previous fault between the bus bar CT and the circuit breaker, with bus bar CT above the circuit breaker, the end fault protection will activate the bus bar inter-tripping logic, tripping all potential fault-feeding breakers. End fault protection was activated because two conditions were met. First, CT current exceeds setting, and second, breaker is open. End fault protection is used for multiple bus bars with CT above breaker. Also for 1.5 breaker setups without CT overlap. It should be used in the case of multiple bus bars where the CT is installed on the bus bar side. It should also be used in a 1.5 breaker setup in cases where the CT is used in a way that does not achieve overlapping. This means if the CT is used in a way that achieves overlapping, there is no need to use in-fault protection. In-fault protection reduces trip time. Can the occurrence of switching to voltage affect the end-fault protection? Assume the CT is installed on the bus bar side. If this circuit breaker is open, then the end-fault protection will be ready to issue a trip decision and will wait for a current to pass through this CT. If there is an external fault already present and a command is given to close this circuit breaker, an electrical spark will occur at the moment of closing. The inspiring leader of a nation's renaissance, Can the occurrence of switching to voltage affect the end fault protection? Let's assume that the CT is installed on the bus bar side. If this circuit breaker is open, it means that the end fault protection will be ready to issue a trip decision and will wait for current to pass through this CT. If there is an external fault already present and a command is given to close this circuit breaker, an electrical spark will occur at the moment of closing, just before the circuit breaker signal indicates that it is closed. When the current flows together with the open position in the circuit, it will respond accordingly. It issues a false trip signal for the circuit breakers. If the CT is installed on the line side and a command is given to close the circuit breaker during a bus bar fault, the end fault protection will activate and send a false trip signal to the remote circuit breaker. Though the fault isn't on the line, this happens because the circuit breaker hasn't reached the closed position yet, sending the trip signal prematurely. To prevent this, inform the relay to block end fault protection if a fault occurs during manual close mode. Ensure the manual closed circuit breaker is correctly installed and tested. If the signal fails, it may cause incorrect operation as the fault current won't be read. If a number of faults occur while there is a manual closed circuit breaker, which represents a switch into fault condition, we need to block the end fault protection. This requires that the manual closed circuit breaker going to the bus bar is installed and tested correctly, no doubt about it. If the signal doesn't reach, this means that there could be an issue and it could lead to incorrect operation. In this case, it will operate incorrectly because the current feeding the fault won't be read, especially for this protection. This means that it can happen there and can lead to incorrect operation in a case where it will operate incorrectly. This is because the current feeding the fault won't be read, especially for this protection. This is because for this protection, it is still considered open, and the end fault protection will incorrectly trip all the circuit breakers connected to the same bus bar because it sees that the circuit breaker is open and is reading the current, even though the fault is on the line and not on the bus bar. With that, we will conclude today's lecture by explaining most cases of low impedance differential protection. Join us in the next lecture where we will explain the details of high impedance differential protection. Take care, and peace be upon you.